Okay, so now let's talk about the dual basis. What do I mean by dual basis? Okay, so assume the matrix A is invertible. It means what? It means that it's a square matrix. So B is an inverse of A. B is equal to A inverse. And A1, A2, AN are the columns of A. So matrix A is invertible. This means that it has a linear independent columns. And B1 transpose, B2 transpose, all the way to Bn transpose are rows of B. So we used this notation in the past before. So let's take a look at the definition of A and B. A is this. So these are, each of these is the columns of matrix A, and these are, each one is rows of matrix B. Okay. So matrix B has independent rows since it's invertible. Matrix A has independent columns since it's invertible. Okay. So since A is n by n is a square, it has n independent linear independent columns. So columns of A form a basis for n-dimensional space. So I can represent any n-dimensional vector based on linear combination of columns of A. Okay, very good. So let's say that this vector x I want to represent as a linear combination of A1, A2, these are columns of A. And this B1, beta 1, beta 2, they are a scalar. Now we can use this concept of dual basis to estimate these scalars, this beta 1, beta 2, all the way to beta 1. How do we do that? We know A is invertible, and inverse of A is B. So we know this equation is correct. AB is equal to identity. At the same time, we know X is equal to beta 1, A1, beta 2, A2, all the way to beta 1, AN. So what I'm going to do, I'm going to say that this X is equal to identity times X, right? When you are multiply identity by any vector, you get the vector back. So, and then I'm going to go ahead and replace identity by AB. That's what I'm going to do here, because AB is identity. So let's see what we get. This is A based on the column representation. This is B based on the row representation, multiplied by vector X. Okay. So then what do we get? What do we get for this X? Well, what we're going to do, we're going to go ahead and first multiply this X by this column vector, or this matrix B, right? Which is represented as a block vector, block column vector. When you do that, what you get is that X, this X, is equal to what? Is equal to B1 transpose X times A1. What do I mean by that? So when you do that, you're going to go ahead and multiply X by each of these. So you get B1 transpose X, B2 transpose X, all the way to Bn transpose X for this one, right? What is B1 transpose X? It's a scalar. B1 transpose, remember B1 transpose is a rows, right? So B1 transpose X is a scalar. Remember, it's a dot product is a scalar. Now, and then, so B1 transpose X means dot product of the B1 and X is a scalar. Times A1, A2, all the way to AN. Well, guess what? This is just a matrix. This is just a matrix A, right? So we want to multiply a matrix by a vector. Again, the intuitive interpretation that we have is equal to linear combination of columns of matrix A. What it means is that B1 transpose X times A1 plus B2 transpose X times A2 all the way to Bn transpose X times AN, right? So consider this B1 transpose X to be like a new X. We had X1 times A1 plus X2 times A2. This is like a new X. This is just a weight, right? It's a scalar. So that's what we get. And that's what I did. I call this B1 transpose X as a beta 1. This B2 transpose X as beta 2. And Bn transpose X as beta n. Okay, good. So in a sense, I can represent X to be beta 1, A1 plus beta 2, A2, all the way to beta n, AN. And that's what I have here, right? That's what I was, what is it? That's what I have here. Yes. Right? But now I know how to get the beta. So I know beta 1 is equal to B1 transpose X. And beta 2 is equal to B2 transpose X. right? In a sense, I have a way to find the coefficient of columns of A. Maybe we want to represent the X based on a dual basis. So we know that any n-dimensional vector X can be represented as a linear combination of the columns of a matrix A, since they are independent. Now I know inverse of A is B. So how can I find the representation of this beta 1, beta 2, right? When I have the matrix B readily available based on this. Okay. Now, if you look at this equation, these betas, let me just write a little bit more. This beta n is equal to Bn transpose X. Remember what I said? I said this B1 transpose, B2 transpose, all the way to Bn transpose, they are like rows of matrix B, right? So in a sense, you can group them and write B or beta, this is beta vector, vector of beta, is equal to B transpose, this is B, right, times X, right? Just write what I have here in a matrix vector notation. But remember, what was B? B was nothing but A transpose. Sorry, A inverse, right? So this one will be this. A inverse transpose times X. So this is a way to remember this is beta and this is B or A inverse, right? So this is a vector of coefficients. Okay. So this dual basis is used to find these coefficients beta 1, beta 2, beta n. When you have the inverse readily available, or it's easy to calculate the inverse, one way was to use always a projection, right? This is another way to find these coefficients. Okay. Because if you have the inverse available, then calculation of this dot product is fairly easy, beta 1, beta 2, beta. Okay. Now let's move to the very important concept, which is the pseudo-inverse. So if matrix A is left invertible, this means that it's a linearly independent columns, right? Then we claim that A transpose A is invertible. If matrix A has a linearly independent columns or left invertible, remember these two are equivalent, then it has a then A transpose A is invertible. Or if A transpose A is invertible, then matrix A has a linearly independent columns or is left invertible. This is if and only if a statement, right? Let's see why this is correct. By the way, this A transpose A, this is usually known as a Gram matrix. Okay. So let's start from this direction first. If columns of A are linearly independent, right? If columns of A are linearly independent, we want to prove that A transpose A is invertible. Remember what I said? I said if you want to prove independence, invertibility, you always start with some sort of matrix times a vector equal to 0. We start by A transpose A, X equal to 0, because we want to prove that A transpose A is invertible. Okay, so we just need to know why we are starting with this. Okay, so we multiply by X transpose from the left side. This is a very famous trick. It's good to see this at least once. So if you do this one, what you get is this. You get X transpose A X equal to 0. Look at this equation for a while in the red. What is this equation? Is nothing but this. AX transpose AX equal to 0. But this is nothing but norm of AX squared equal to 0. Remember the properties of norm? Right? We talk about normal matrix or normal vector. Doesn't really matter. This is normal vector because AX is a vector. Norm is always done negative. Or is always either 0 or greater than 0. And 0 only happens if the argument inside the norm is actually 0. So I want AX to be 0. So I want AX to be 0. But wait, A has a linear independent columns. So AX equal to 0. This means X equal to 0. So we prove that A transpose A, X equal to 0 only happen when X is equal to 0. This means that we only have a trivial solution for that. This means that A transpose A is invertible. Okay? And that's what I have here. A transpose A is invertible. Now, we would like to prove that if A transpose A is invertible, then A has a linearly independent column. Okay, let's take a look at this argument that I have. I want to prove if A transpose A is invertible, then A has linearly independent column. Independent columns. Okay, so let's go back in your philosophy or maybe logic classes. Take this one as P, take this one as Q. We want to prove P gives Q. One way to prove this is that not Q, this is equivalent to not Q gives not P. This is one way to prove this type of logic, right? So we want, instead of A transpose A invertible, then A has a linear independent column, I can say that what if A has a dependent column, and then I want to prove that A transpose A is not invertible. If I can prove this one, then I prove P gives Q, right? Let's do this one. What if A has a linearly dependent column? Then AX equal to 0 has non-trivial solution. Means that it has a solution besides X equal to 0. Okay? Or has a non-trivial null space. Okay. Then what I'm going to do, I'm going to go ahead and multiply AX equal to 0 from the left side by A transpose. From the left side. Okay? So then I get A transpose AX equal to 0. Right? For some X that is not 0. So still this one, because the X is not changing. So AX equal to 0 is for some X. Let's say, I don't know, 1, 2, 3. Right? Okay. If I multiply that by A transpose from left, I still get 0 for the same X. Right? Doesn't really matter. I just multiply this one from the left by A transpose, but the 0 multiply A transpose from the left or right is still 0. Right? So A transpose A, X equal to 0, it still has a non-trivial solution. This means that columns of A transpose A are linearly dependent. Therefore, A transpose A is not invertible. Okay? So columns of A transpose A are linearly dependent. Okay, so what did we prove? We proved that if A has a linearly dependent columns, not Q, right? Then A transpose A is not invertible, not P. So I actually proved this one. Okay, good. So why did we prove this one? We proved this one to find the left inverse of matrix. Remember in the first part I talked about the matrix C to be left inverse of A. If we multiply it on the left side, we get identity, something like this. But I never said how to calculate the matrix C. We just said this C exists if matrix C is tall or a square, right? Now we want to give you an equation for that. It turns out the left inverse of A is equal to this. A transpose A inverse times A transpose. So why did I prove that A transpose A is invertible? Because of this equation. If it's not invertible, then A transpose A does not exist. So all we did here just to prove that left inverse only exists if A transpose A is invertible. Okay. Now, how do you remember this equation? What are we trying to do? We are trying to find the left inverse of A. What does left inverse mean? This means that this matrix is A and this is identity. I want to be able to multiply something with this matrix A to get identity. If I know that this is A transpose A inverse, I want to be able to generate exactly the same thing here, but without inverse. So this one should be A transpose because this is the same as this one, only this doesn't have an inverse. And that's one way to remember this equation. Okay, good. So this left inverse of a matrix has a very famous applications in different problems. It's actually very important for different machine learning, optimization, and signal processing problems, right? This is this usually denoted by this symbol. So what this is defined for a tall matrices or a square matrices because it must be in left invertible. But what if A is a square? Because we proved that if A is a square and has a linearly independent column, then A has an inverse, right? So then we can call it A inverse actually. So if A is a square, then A inverse exists. Now let's take a look at what happens. Let's take a look at A transpose A inverse A transpose. This is equal to this. Now, if A inverse exists, I can just go ahead and use the property of A inverse here. This is equal to A inverse, remember, A negative transpose. We can switch them. So A transpose inverse is equal to A to the power of -1 transpose, right? Times A transpose. These two cancel out and I get A inverse. So if the matrix A is a square, still our intuition or our equation work, right? Oh, but the general formula is this one, this equation. Okay. Now, what if the matrix A is right invertible? If matrix A is right invertible, then it has a linearly independent rows, right? One way to look at this one is that if matrix A is right invertible, then A transpose is left invertible. We proved it in the last video, right? Therefore, A transpose has a linearly independent columns, right? And therefore, A has a linearly independent row. So this is the thing that you should be very familiar with that. Now, what we did for the previous case, for AX equal to 0 has a linearly independent column, we can do it for A transpose because A transpose has a linear independent column. So A transpose X equal to 0 only happens for X equal to 0. Therefore, go ahead and multiply this from A from the left side, right? So we get A transpose X equal to 0 only for X equal to 0. This means A times A transpose is invertible matrix. By the way, something that is very important is if A is n by n, A transpose is n by m. So A transpose, right? A transpose or A transpose A are always a square matrices. That's why inverse makes sense. They're always a square matrices with different dimension, of course. Like A transpose is m by m square and A transpose A is n by n square. Okay. So in that case, we need to have some sort of A transpose when we use this inverse. And that's why this is the right inverse of a matrix A, because we have A transpose. Because A transpose has a linearly independent column and is invertible. A transpose A in this case is not invertible. Okay, good. So this is the definition of right inverse of a matrix. How do you remember that? Right inverse is this A. You multiply by some quantity, you should get I. You know A transpose for a right invertible matrix is invertible. So you will have A transpose and negative. So you need to generate the same thing that you have here. Here, you have one A. So what if you add one A transpose here as well? So this is called the inverse of a matrix. This one. A transpose inverse. And what if the matrix is a square? Then the pseudo-inverse, this is called pseudo-inverse, should be equal to A inverse. Let's see whether we get the same thing or not. So if the matrix is a square, we get A transpose. Now, if we use the properties of inverse, we get A and A inverse. But these two cancel out each other and we get A inverse. So this equation works even for the square case. And we get the famous A inverse back. Okay, good. Now, what if I want to use them? What if I want to calculate the pseudo-inverse of a general matrix? What does it mean? What if I tell you that I have a square matrix that does not have linear independent column? What if I have a tall matrix that doesn't have linear independent column? Or what if I have a wide matrix that doesn't have a linear independent row? It is possible, right? Can I define a pseudo-inverse still for a matrix? Yes, right? In that case, the way we define the pseudo-inverse is using a Tikhonov regularization. Or we call this one Tikhonov regularized inversion. What is that, right? Tikhonov was the name of person that came up with this. Tikhonov regularized inversion is the minimum, or the minimizer actually, right? Is the minimizer of this equation. Norm of ax minus b square plus lambda norm of x square. This lambda is weight that we have is greater than 0. So we want to find the minimizer of this, right? This equation. So regularization, actually, you have seen it a lot. This is called example of L2 regularization. So this is because this is the norm 2 of a matrix. We added to that in order to get a non-singular, actually to get a non-singular answer, right? Because we know that the actual pseudo-inverse does not exist. The pseudo-inverse that we derive in the last part, it actually does not exist. Okay, good. How do you find the minimizer of this? We have to take a derivative respect to x and set it to 0. We are minimizing respect to x. Lambda is just a parameter. Okay, so we use the definition of the norm that we have. Norm of x squared is just equal to x transpose x. We are gonna replace them here, and we simplify this. First, we're gonna go multiply these parentheses together, right? We get j. J is just this. It's called objective function, and we take a derivative respect to x. Let me walk you through that. This is called quadratic equation, right? So when you have an x transpose ax, or let's say x transpose bx, the derivative of this respect to x in general becomes b transpose b times x. But guess what? A transpose A is always symmetric, right? If you have an A transpose A, if you transpose that, you always get itself. And that's why I get A transpose A plus A transpose A. So from these two, when you take a derivative, they are the same, by the way, because the result is a scalar, right? So you can add them up. You get this negative 2A transpose B. And this one is what? This one is nothing but when B is replaced by identity here. So what you get here, you get identity transpose I plus I. So you get 2x. So here we get 2 lambda x because we have a lambda as well. If you set it equal to 0 and simplify that, you get x equal to this, right? So this is going to be the solution of this equation, right? It's a minimizer of this expression. The x is going to be minimizer of this expression. But wait. X was the solution to this problem. What was x? X was solution to this problem. Ax equal to b. Right? X was the solution, and we knew that we cannot really find the inverse. Okay, so when we had an inverse, x was equal to A inverse b. Okay, when we had a left invertible matrix, a still would be equal to x would be what? Or right inverse, it could be equal to A pseudo inverse b. So in a sense, the pseudo inverse of a matrix is equal to this, right? The b is not there. That's the pseudo inverse of a matrix, and therefore we define the pseudo inverse of a matrix. One way to define that is going to be based on A transpose A, right? Based on A transpose A, it's going to be A transpose A lambda to the A inverse times A transpose. When limit of lambda goes to 0, because lambda is a small value, we add it. We add that just in order for this matrix to be invertible. You see, remember, this A transpose A is not invertible, right? We said that A transpose A has a linearly dependent column, right? Or we say that what if A has a linearly dependent column? It's possible, right? If it has a linearly dependent column, then A transpose A is not invertible. So lambda is just a very small perturbation because we don't want to change the solution by much, right? It's a very small perturbation until we get an invertible matrix. And that's why this says the lambda should go to 0. So that's one way you define this pseudo-inverse. It turns out another way, usually you get it using kernel trick, is to define it based on AA transpose, right? Remember A transpose A was for left invertible matrices. Now we have the AA transpose for right invertible. These two are the same. You can define it like this. A transpose plus lambda I inverse. Again, what is this should be also lambda I. What is this? A lambda is a small value, a small perturbation you add to make sure that this quantity is invertible. Right? So that's another way you can define the pseudo-inverse when lambda goes to 0. So these two equations are general way you can actually solve the pseudo-inverse of matrix. When we have a linearly independent columns for A, right, then A transpose A itself is invertible. Then you can set the lambda to be 0, right? And then you get the famous left inverse of a matrix, pseudo-inverse of a matrix. And the same thing for the right inverse of a matrix. Okay, very good. So that's what I have for this video for inverse of a matrix. Thank you so much for watching. See you all in the next video.